first sort of an announcement, and that is, right now, because we're doing this waitlist system, I know I have several students asking me about opportunities to enter the class. We are holding registration at 75 in both sections. We are going to be offering, well, it's not official yet, but we're very likely going to be offering 2 large sections of 370 again next semester. So if you don't make it in this semester, next semester has a great opportunity to get in. Okay? So as far as waitlist is concerned, I don't have control over students dropping beyond what I did the initial length, because everybody's been attending, and at this point it's a matter of those students who decide to drop, they drop, somebody gets added in, but I'm not going to increase the number of seats. Okay? So that seems to be the biggest question so far, but beyond that, now do we have any other additional questions? No? Okay. Sure. Let me do that. In that case, let's pick up. Yes?
Did you ever post the exam dates?
No, I didn't post the exam dates, and assignment number 1, I am this close to publishing. So I will publish that here in the next day or 2.
Wait, both of them? Or just
both. I'm going to have assignment number 1 posted.
Yeah.
And I'll also be posting our schedule for exams and assignments.
Thanks.
Yeah.
Is the assignment 1 going to use for logic work?
Yes, it will. Assignment 1 will. All assignments will be using logic, including assignment number 1.
Can't wait.
Excellent. Great answer.
I'll buy it. I'll buy it.
So again, those of you who haven't formed teams of 2 yet, you want to do that. And I would recommend doing that before you leave tonight. That's the best way for you to form a team, is that when you leave tonight, don't leave unless you're in a team. Okay? And then you can kind of mull around. Other students looking to form a team, they'll be mulling around too, and you just kind of figure out teams from there. Okay? Yes?
Are you going to do attendance again?
Nope, I'm done with attendance.
What are you here?
I'm done with attendance.
Should have done it now.
It's all up to wait list now. Other questions? Yes. The C version? So LogicWorks itself is a simulator that helps us work with the, and I'll put it up here a little bit so you can get a visual of it, but it helps us understand what logic diagrams are like, what logic is like. If everybody, it's a big room, I think everybody wants to hear, so if we can be quiet, please. Others might want to hear the answer to this question. The question was about LogicWorks versus a programmed language. And the idea with LogicWorks is that it is a simulator. It is a simulator specifically designed to help us manipulate visually as well as through its own language, VHDL or Verilog, to be able to program logic. Okay, so you can get a hands-on visual, here's how logic works, as well as the descriptive languages of being able to program logic and seeing how it works as well. And you can also generate it from the simulator. So I'm going to be using LogicWorks for all of our assignments for that main purpose, not necessarily a compiled language. I did mention that you really do need the Windows version, and it's because the Windows version supports VHDL and Verilog, whereas the Mac version does not. So that doesn't mean you have to run out and get a Windows machine, because you can get, if you have a Mac that is, obviously if you have a Windows machine, you're sitting there fat and happy and saying, yeah, this rocks. But those of you with Mac or Linux are saying, but, no problem, because you can get either a virtual machine and run LogicWorks in a virtual machine. Actually, that's really your only option. There's one other, but I'm not going to go there. So for Mac users, you can get, there's a free version put out by Cisco, and there's versions that you can pay for as well. So you can get a Windows-hosted environment on your Mac OS or your Linux machine, so you can run the LogicWorks 5 version for Windows, so that it fully supports VHDL and Verilog. Okay? Other questions? Yes?
the software comes with a CD. You know, of a way for downloading it. Most of the laptops come with a CD-ROM
For a CD for what?
for installing software. Well, that's how I got into book.
So you could download LogicWorks. If you go to the vendor themselves, you can actually purchase it online and download it. And they're actually cheaper than the Amazons and a couple of the other sites I've seen it posted on as well. So yeah, if you do those sources, you can download it and start using it right away.
Say if I like copy of LogicWorks on my computer and then I develop on 2 different computers, is that gonna be an issue? Like,
I don't care. I don't care what machine you develop
oh,
on.
like how does that work? Does that code like I'm assuming you get a key. Does that key only work for my computer?
Oh, as far as if you purchase it on one machine and use it, LogicWorks says that they support you purchasing it once and loading it on multiple machines. And the license
as you're not
key, I
using
think,
the
is
same
just phoning home every time you launch it to make sure it's not already ready.
Oh, so like for example, like if me and my partner wanted to share one key, would we do that?
Maybe. Again, if you're launching it once, you're not trying to launch it simultaneously, I think
Yeah.
that'll work. Yeah. Yes.
So when we turn our homework or assignment out for partners, do we turn in 1 copy or 2 copies?
You're going to turn in 1 copy.
There
That'll
you
be
go.
part of the turn-in instructions that you'll get.
Only
We're
one
going to
copy.
use Blackboard, just to go ahead and talk about that part of it. We're going to use Blackboard just like we're using it now for distribution of assignments and slides and everything else. I'm also going to use it for project turn-ins. So what will happen is you're all working in teams of 2. So when you turn in your project, you'll turn it in on one. One of the 2 of you will say, I'll do the turn-in, and you'll turn it in for inside of your Blackboard for your assignment. This is really important to stress, but when you're doing documentation, it's always important in your documentation to put names and red IDs and class numbers and section numbers so that everybody can get credit for their work. And so that I know that it's this section and not somebody else turning it in from the wrong section accidentally or something silly like that. So you, at a minimum, both names, both red IDs, class name, section, dates. Okay? I'll put that in my instructions for the turn-in as well. But yes, you'll only turn it in on 1 account. Since you're going to have both names and both red IDs and the documentation, I will be able to, or my grading assistant will be able to assign that grade to both accounts. Okay, but only one turns it in. Please do not turn it in on both accounts. If you're going to say, wow, I'm just going to make sure he's going to turn it in and she's going to turn it in, we'll make sure we get a copy from 2 accounts. Please don't do that. That just creates more work for us. Turn it in just 1 account. As long as your documentation has both names and red IDs, you are good. Even if it doesn't, we can fix it later, but there'll be points deducted for not following instructions. Okay? Are there any questions? Other questions? By the way, I'll also put in some instructions for something called a README file. So those of you who've had me before saying, oh yeah, I know what this is. For those of you who haven't, maybe you're familiar with files named README or not. But basically what happens is in software projects typically will include a file called README. README is kind of an ad hoc document as far as what are the formal requirements for a document called README. Really is ad hoc. But it generally means instructions on how to build, compile the project, and run it, as well as what did I do since the last bug fixes, or if it's the first release, user beware, I'm sorry, great software, use me, right? So anything you want to tell the system administrator, the person who's configuring the tool, in this case the instructors and graders, you want to document inside the README file. So obviously it's going to have 2 names, 2 red IDs, a date, the name, and class and section, all that good stuff. But it's also going to have some additional details in there. I will have a guideline. If I haven't posted it yet on Blackboard already, I will be posting it tonight on what a README file is and what I expect to have in it. Okay? So every project will include one file called README, and it's typically a text file. So you use any text editor. If you really want to use a word processor, you can. I'm okay with that. I support most formats. But it's typically our text file. But that's going to be required in addition to the project files, the other project files that you're focused on. Okay? Other questions? Okay, very good. Before we get started, I realize there's one thing I didn't mention on first night. It's worth bearing out here, is that we're a very large class, and I know the 5:30 through 6:45 hours kind of between where you might normally eat dinner and stuff like that. So I understand bringing drinks and maybe a couple snacks into the class, but refrain from bringing dinner into the class, okay? Yeah, I know it's very distracting to other students, and then we have other students with dietary issues and stuff like that. So save the meals for after class or have them before class, but let's not make this dinner theater, okay? All right, so enough of that good stuff. How about what we came here for? There we go. Which is this architecture stuff. And we talked about all the basic introductory stuff that we need to talk about. But now we need to dive down into the number systems. That's what the rest of chapter 1 is. We're finishing up chapter 1 tonight. We're going to rock right into chapter 2 on next Monday, so you want to prepare for that. Really, this should be review. We should have covered all this stuff before, but I want to cover it tonight to make sure we all understand it, because it's going to be very important to us for the rest of the semester. Okay, and that is, when we're working with systems architectures, we're typically going to be working in one or maybe 2 or 3 or even all 4 of these different numbering systems. So you should just know really well binary, octal, decimal, and hexadecimal numbering systems. They should be pretty much second nature to you. Now, having said that, there are parts of it that you probably don't think of. I mean, you know, most of us know how to interpret 4 bits into a hexadecimal number, 3 bits into an octal number. That's okay. I think we're pretty good with base 2, except I've learned that for some reason, even up in the upper division classes, we tend to forget some of the base 2 properties. So we're going to focus on that here just a little bit tonight. You're going to brush up on it because it's great test question stuff. Right? Just in case you're wondering what could be on the test. Well, yeah, these may be great test questions, right? So let's focus first on base 10, otherwise known as decimal, which all of us do in our sleep, right? Because we don't like to do math in our wakes. No, because we love decimal systems. So obviously, when we talk about a numbering system, we have to know its radix. We have to know what numbers are part of the system itself. Okay, so the base 10 system, its radix is 10, and it consists of those digits, 0 through 9. Okay, so a number like 24.3, when we don't include the subscript number, we assume it to be base 10. Now, all of us know that assume is an acronym, right? Okay, well, you figured it out on your own. Okay, so it's always bad to assume. Well, in this case here, we can say you may assume. It is safe to assume that any number you're looking at, if it does not have the designator for the base system on it, you can assume it to be base 10. Now, since we're talking about different numbering systems, I'm explicitly declaring it because I want to explicitly differentiate it from the other numbering systems. So it never hurts to put it on there, but if it's missing the base, you may assume it's base 10, and that's base 10, and that's one of the few times you can ever assume anything in computer science, right? The resounding right came back in. Thanks, there was 3 voices. All right, so radix system. So here radix is showing us we have the decimal indicated after or prior to the last digit, and everybody knows that everything up here is a whole number of some power, and everything down here is a fractional part, right?
Yes.
Now, it's worth saying because I think I've said it before. I think I said it first night, but it's worth revisiting. Being or becoming a scientist means you're able to explain things. Okay, being able to work a calculator and getting an answer to a problem is something that most anybody here can do. Being able to program the calculator, which means you understand how all of these different components, what each of those components are of the number, and how to operate them and how to calculate them, is what will differentiate you. Okay? So when we look at a number like 24.3, you're automatically interpreting that to say 24.3, it's almost 25, it's more than 24. Okay, got that. But let's take a look at how you literally interpret that. What we're really saying is that we have 2 in the tens place, 10 to the 1, 4 in the zeros place, which in this case is 4 times 10 to the 0, which is 1, so that'd be 4, right? 2 times 10 to the 1 would be 20. And we're adding 20 to 4. And then we have the fractional piece. Now it's fractional, so our exponent's going to go negative, right? First position over, minus 1. So 0.3. So that's how you get the 24.3. So reminder stuff, right? Awesome. Let's take a look at binary then. Okay, so binary system, base 2, radix 2, is comprised of the following 2 digits, 0 and 1. Surprise there? Everybody gets it. So if I gave you a number like 1101.01 and I tell you it's a base 2, then you take a look at that and say, okay, that's cool. 1101.01, great. But I would then ask you, well, what number is it in base 2? And everybody remembers how to convert it, right?
Base 2.
Well, it's just like we converted our base 10 number. We're going to take this 1, right? And we're going to multiply it times what? Our base
2.
system
2.
to whatever power. What power is this?
4. 3.
3. So it's 1 times 2 to the 3, which we all know is 8, right? And the same with this one, times 2, 0, 1, 2 to this 2. This one we skip over, 2 times 2 to the 0. Now here it gets a little interesting, right? Because we have the decimal place. So we have decimal and we have this 0, so we're going to skip over the minus 1, right? And then we have this, which is 1 times 2 to the minus 2, which we know to be 0.25, right? Minus 1 would be 2 to the minus 1 is 1/2, 0.5. 0.25. 2 to the minus 3, 0.125. Dividing each one in half, right? Each one gets smaller by half. So I now add these together. 8, 12, 13.25 is my decimal number from 1101.01. Right? Cool. Okay, we're feeling good, right? That's making sense. It's bringing back, it's refreshing brushing off cobwebs, refreshing some brain cells, right? Good. Okay, octal. So octal. Base 8. Radix 8, comprised of these digits, 0 through 7, right? So if I give you a number like 247.4 base 8, you could convert that, right? Because you have 2 times what? 8 to the 2. 8 to the 2. 2 times 8 to the 2. Plus 4 times 8 to the 1. Plus 7 times 8 to the
0.
0. 0.4 is
8 to negative.
4 times 8 to the negative
times
1.
8 to the minus 1. So there you go. 2 times 8 to the squared, 2 times 8 to the 2, 4 times 8 to the 1, 7 times 8 to the 0, 4 times 8 to the minus 1. So 8 squared.
Oh, 64.
64 times 2, 128, right? 8 to the 0,
1.
1, 1.
Yeah?
Yeah. There's your 7. Did I skip anything? That one? Okay. 8 to the 1,
8.
8 times
4.
4 is 32, so you have 128 plus 7 plus 32. It's all commutative, right? It's addition. Remember commutative, associative, distributive, all those laws? Don't forget them, you're going to use them. Plus 4 times 8 to the, what's 8 to the minus 1? What was 2 to the minus 1?
0.5.
0.5. What was 10 to the minus 1?
0.1.
1.
0.1.
0.1? So 8 to the
No,
minus
okay.
1, 0.5 times,
No, 0.125, something like that.
there you go, 0.1 times 4 is 0.4. Add them all together, 167.5 and base 10. 10 minus 1 was 0.1, 8 to the minus 1 was 0.1.
125.
Ah, good. Okay, that leaves hexadecimal. Base 16, radix 16, comprised of the alphanumeric set of 0 through F, right? So if I gave you a number such as 146.A in base 16, you could easily convert this to base 10 as well, right? You would start off with
1 times 16 to the second.
1 times 16 to the
Second.
2. 2. 4 plus 4 times
16 to the
16.
to
first.
the
First.
1 plus 6 times 16 to the 0. Decimal.
10 times 16 to negative 1.
A or
A.
10 times 16 to the minus 1. There you have it. 16 squared is 1, 16 to the 1, 4, 16 to the 0, 6, 10, 16 minus 1. That's how we get that number. Any questions? All review stuff, right? Alright. So one of the things you want to take away from tonight is that 0 through 16 in all 4 of these systems, you should know like that. Like you might use it on exams and stuff like that, right? But working in computer science, this day forward, everything you do, anybody can ask you a number in any of these base systems, 0 through 16, and you can give them that answer. That's just one of the things you know cold, right? Just like certain powers of 2, right? You're going to know certain powers of 2 up to a certain level anyway, like 2 to the 8th. 2 to the 8th is easy. Beyond that's not that hard either. But some of these things you just know. Okay, don't stop and think about it. Don't stop to calculate it. These are things you just know. And consulting a calculator for one of these things is a crime. All right? Just don't want to be caught doing it. All right, so next thing we need to be concerned about is our range of numbers that we have to work with. Okay? When I talk about it this way, I'm talking about it this way because we have to be concerned with representation. We have to be concerned with representation. Needs to know, of course, the base number, the radix, and the decimal fractional component. But we also have to be concerned with how many bits we have to represent a number with and how to represent that. So for example, in a system such as a system where we can represent 3-bit numbers, kind of like an octal number, right? This has 3 bits. Okay, from the range of 000 to 111. Well, in the decimal system, it's 0 to 7. So we're counting to 10 without a couple of fingers, right? So we could do that. But we also need to be able to convert it to 2 to 3, obviously, because that gives us 8, which is 0 to 7. The other way we can represent that, since we are going from 0 to 7, is 0 to 2 to 3 minus 1, of course. Now, it's, like I said, it's important to know how to represent these numbers because it's important to know how to calculate them, both what the actual number is as well as what its limit or range is. Okay, so it's important to remember, this is just reminder stuff, but it's still important to remember at this point that when we talk about the range of numbers, since we're starting at 0, we're not working with ordinal numbers, we're starting at 0, okay, we're worried about 0 to n minus 1, not 0 to n or n to 1 to n, okay? So 0 to n minus 1 gives us to the n unique numbers, okay? We're going to represent it with 0 up to the n minus 1, regardless of what that system is. For fractional points, we're going to start with 0, and we're going to go to the n minus 1 over 2n. That's how we get those different calculations for the different base systems. Now, working with different numbering systems has some easy ways of us converting between one number system and another. It's not really uniform because some conversions are pretty easy. It's actually pretty easy to go from base 2 to base 8, base 2 to base 16. We saw it really wasn't that hard to go from any of those bases to 8, 16, or 10 to base 10. Base 10 to base 10, oh well. 2, 8, 16 to base 10. Wasn't that hard. Base 2 and base 16, excuse me, base 2 to base 16 or base 8 is also fairly straightforward, okay? And it's basically taking your series of bits and dividing it up into your different numbering systems. For example, let's go to the next one. I think it's a little easier to see on, oh, I guess I have it further down. Okay. Let's go ahead and just use the board here for this one then. So for this number here, where we have this division into hex, which was 1001, 1110, decimal 0101. Okay, converting this into hex was pretty straightforward because even though this is a binary number and we looked at how we could convert it from binary to decimal, we're saying instead of going to binary to decimal and then going to decimal to hexadecimal, I want to go straight to hexadecimal from this number. Well, it's pretty easy to do because starting at the radix, I just simply cluster my numbers into the 4-digit system of a hexadecimal system. And at that point, I'm just doing a straightforward conversion, right? E1110 is E. And for those of you struggling how to remember E, well, it's just one less than the maximum, which is F, right? Okay. And this one, which is
9.
After all, everybody knows that's 8, right? Okay, so one more is 9, that's easy. But again, all these numbers, you just need to know these. Right? What about this one?
5.
5. Is that the same in octal as it is binary? I mean, hex? Well, yes and no. It's a fractional part, right? So if this were a octal number, that 1 would fall into the next digit. So this would turn into a 2 in a base 8 system. But in hexadecimal, which is what we were working with here, yeah, it's a 5 because I'm using all 4. So while we're at it, let's go ahead and erase it. Let's go ahead and do this as an octal number. To convert this into an octal number, I'm going to do something similar. But instead of clustering these in a range of 4 digits, I'm going to cluster it in a range of 3 digits, right? Because octal numbers are in the range of 0 to 7, which is where we get the 8 in base 2. And that, to represent that, takes 3 digits, right? And in a binary system, I have zeros and ones. So 3 digits, zeros and ones. So if I clustered these, starting at the radix, into 3s, it would look like this. Now notice I have 3, 3, 2. So this next digit is implied to be 0. So I could just go ahead and 0 fill it. Coming from the radix, I then have 3, 1, and again it's not specified, so it's implicitly zeros. And I can now convert this. This is a 6. This is a 3. This is a 2. And this is 2.
Is that a 4?
That's a 4. Exactly. So you have 236.24 in base, octal, base 8, which was 9E.5 in base 16, which was 1001110.0101 in base 2. Right? Easy peasy. Methodically. Work these methodically. Don't try to take shortcuts. If you take shortcuts, you'll make mistakes. Okay, you'll make errors. Right? So don't take shortcuts. Shortcuts lead to errors. So knowing that, you can now convert any of these. Right? Of course you can. The confidence level in here is growing by the minute. I can feel it. You're going to start getting the feedback. You're going to be confident in yourself. You're going to start providing answers. It's going to work. I know it is. Okay. Yes, you can do this. So the octal system. We actually walked through this already, but since it's here, right, radix is 8. We have 8 digits. 0 through 7, which is 2n minus 0 to 2 to the n minus 1, right? So we have, n in this case is 8, 2 to 3 minus 1, 2 to 3 minus 1, which is 8, minus 1 is 7. That's how we get 0 through 7. So if I took a number like 275 base 8, just like we saw in the previous example, there's 2 times 8 squared plus 7 times 8 to the 1 times 5 times 8 to the 0 is 189 base 10. Everything being represented by bits, just like we talked about. Now, let's walk through the algorithm a little bit. We already did this a couple of times, but let's talk about the algorithm. Converting from one base to another, the first thing you do is take the whole integer part and convert it. Then you take the fractional part and you convert it, and then you join them at the radix point. Yes, we've already done this a few times. But now we're explicitly stating it because one of the things you want to do as computer scientists is be training yourself into either developing algorithms or understanding algorithms so that you may code them. Yes?
What's the radix point?
That's what we call the little decimal character. So the radix point, that's why we're talking about the radix of each of these different numbering systems. Okay? So here's the radix point.
Decimal point.
Here's the radix point here, here.
Thanks.
Yeah. So now the formal definition, we understand it. We walked through some examples. We could talk to it. You could even code to it now. Okay? Here is exactly how you do it, and that's how we have been methodically going through the previous examples. But not all numbering systems are as easy to convert from to as the examples that we selected. We intentionally selected the easier examples, one, to get you excited about number conversions. Okay? And yeah, it's not so bad in most cases, but the other is that when you start looking at some of the harder systems, you find, oh, they're just the same way, it's just a little bit more math. We love math, right?
Yes.
I thought so. Okay. So, converting the integral part. Repeatedly taking each number, use the divide word, or you can just say, I'm going to take each number, multiply it by the new radix, say the remainders. And then I just repeat that, and at the very end, I assemble it using those numbers in opposite order. We'll look at an example here shortly. To convert the fractional part, we're going to repeatedly take or multiply the fractional component by this new radix, save that integer digit as a result, and the new radix is adding them up in order. So integer part, opposite order, fractional part, in order. Okay? So here's an example to look at. Okay, I want to take the number 325.65 in base 10 and now convert it to hex. Yeah, it's going to be a little bit more work, or at least it seems like it's a little bit more work, because we're doing, oh my goodness, 3 divisions instead of just picking off numbers and multiplying what we did going the other direction. So really it's not that hard. So if I take the whole number, the integer part, 325, base 10, and I simply divide it by the system that I'm going into, which is 16, in this case here, I get 20, 1, and 0. Remainder, 5, 4, and 1. That's the important part there. So the remainder part, 5, 4, and 1. So what that tells me then is I can divide that 20 with a remainder of 5. That's then going to become my least significant digit. 4 is then the next one. 1 is the furthest down. So I'm assembling the whole integer part in opposite order that I'm doing my divisional part for the whole integer. Okay, so I did the 325 part up to the radix, converted it to 145 using just simply by repetitively dividing by the base and taking the remainders. For the fractional part, I'm now going to do just the opposite, right? I'm going to take the fractional part, which is 0.65, I'm going to multiply it times my system, my new system I'm going into, which in this case is 16. Okay, gets this. Therefore, the whole integer part is 10, which is an A. I repeat, 16 times 0.4, 6.4. Whole integer part is 6. 6. And, oh, it does this again. So I now have a repeating number, right? So if I keep doing this over and over again, it's just going to be 0.4 times 16, 0.4 times 16, 0.4 times 16. So the purist, of course, will put a bar over the 66, right? Because that's what's happening. It's just going to repeat forever. So the 6.65 base 10 part goes to A66, since we're doing this in order for the fractional part, A16. So now I just assemble the two together, 145, radix, A66, base 16. I have now converted the number.
Yes. So it's okay to leave it just like 866 now with the line at the top, like you said?
It is okay for what we're doing because we're talking the algorithm and we're talking about a number that we're going to represent in our display systems, which goes from 0 to 16. We don't have the ability to display a bar or any special character symbols. So yes, we would leave it in that form because of those reasons. If this were a mathematics class, you'd be lectured about how evil that was. But we're computer scientists, right?
Are we also going to be doing like hexadecimal, decimal, binary math on the exam?
Oh, sure. Yeah,
How many
all
does-
4 bases, right? All 4 bases are fair game. Yes?
So I noticed, but for the fraction part, I know it doesn't matter, but does that go on forever, like point A666666?
I could continue going on forever, yes.
Okay.
At this point, once I have 2 digits in succession that are giving me the same exact answer, I will stop there. If I see, if it's a different pattern, or if I even suspect it's a different pattern, I might go out further. But if I go out further and it's still supporting just 2 digits, I'll go up to this just to show that's the most significant that I need. Yeah.
How many decimal points should we stop at?
Well, the radix is already determined by the number I'm starting with.
So it's, okay. So in this case, it would be like A7 or A6?
I would leave it A66. It's repeating forever. I'm not going to round. I'm going to truncate. Because if I had rounded this to A7, that would tell me something differently than A66, which says, oh, this could be a repeating number. So I'm going to choose to truncate instead. Besides, my algorithm doesn't say anything about rounding. Yes?
Do you care if we do binary first and then hexadecimal?
You mean do a 2-step conversion?
Right.
Yeah, you should be able to do all of these conversions directly. So yeah, I do mine. Now, how you do it on the fly for your own homework type of stuff, that's one thing. But I would expect you to be able to do any conversion on an exam directly. I'll make a mental note. Make that a direct conversion. Okay. Other questions? All right, let's see what else we got. Ah, base 10 to base 2. Oh, you can do this now. This is just exercise, right? So obviously you would know how to just take the number 54, divide it by 2, gives you a number, in this case the remainder 0. Then you divide it by 2 again, get 13. In this case, it's an odd number, so you're going to have a remainder of 1. Odd number again, you're going to have a remainder of 1. Even number, you're going to have a remainder of 0. See, this is the nice thing about base 2 is you know you're just working with odds and evens, right? Take a base 10 number, divide it by 2, you're going to get a result that's either from an odd or even number that's going to have a remainder of 0 and 1, right? So this one's probably the simplest one to convert into base 10, or in this case we're going to base 2, sorry. The easiest one to convert a base 10 number into base system is 2. And then we simply go down and
Bless you.
for the whole number, the 54 part, opposite order, right? We're doing division and we're assembling it in opposite order. Fractional part, we're multiplication and assembling it in order. So you want to keep those 2 pairs of thoughts going for you. Yes?
I know you want us to convert it directly. Does it matter if we use the same methods as you, though?
Same methods as I. In other words, you will show your work even if you do have a calculator on these numbers,
Yes.
and the numbers and the work that you show will be legitimate.
Yeah.
Yeah. There are some other ways to do these conversions. This is a way. There are some other ways. I do know what they are. So as long as you're using one of those, you're good. If you're making something up and then putting a number from a calculator down, that won't work.
Yeah.
Okay, so here, multiplying it times 2. Odd number times 2 is always going to be even, right? Even number, well, 0, 0, 0, 1. Okay, pretty simple, pretty straightforward. So that's just the 2 things you have to remember. Whole integer number, you're dividing, assuming reverse order, fractional part, you're multiplying, and you're assuming in. Okay, this is the example, this is a slide I was looking for earlier when I was talking about, oh, what if I took a number showing you the difference between going between octal and hex. Again, it's just that grouping of numbers of bits in the system, so 3 bits in octal, 4 bits in hexadecimal, and 0 filling where needed. All right, so conversions. I think we have most of those down. We've got the 4 systems. You can go from any base to any other base directly. Okay? You should be able to calculate those. There's a couple of other systems that you need to be concerned with because we use them very frequently, which means you need to know how to calculate them. One of the very common ones that we use today is BCD, or binary coded decimal. And what binary coded decimal does is it's just like hexadecimal, except you don't use all the digits. Okay? You're going to use 4 positions. You're going to use 4 digits, yes, but we really don't care about the values A, B, C, D, E, F. We aren't going to use them. Binary coded decimal says this is an easy translation between a number representation using binary systems into a digit that we all know and can display and work with. Okay, so yeah, we're gonna waste a bunch of bits. Right? There's going to be 7 more combinations here that we're not going to use, and we're going to say we don't care. I want that extra bit for these 2 extra numbers, 8 and 9, so that I can just go ahead and use this convenient and easy to use numbering system and binary like to give me my decimal number with binary coded decimal. Okay, so it's sort of a headless hexadecimal system if you want to think of it that way. I guess that's okay. The calculating of the number is just like you would calculate hex, except you would never go above the digit 9. Okay? Pretty straightforward, but its simplicity makes it powerful for us to use. And that's why we've adopted it, even though we know it wastes bits, because one of the things you're going to learn in some of your later classes, and I'll just kind of foreshadow it now by saying, one of the purposes of studying computer science is to help us learn how to best optimize the machine. We want to optimize every CPU cycle, we want to optimize every memory location, and we want to optimize every bit in every memory location as much as we can. Optimization is a big, big part of why we study computer science, so we can get the best performance both from speed as well as footprint or memory usage is concerned. I'm concerned with both of those things. And that's why it sounds really, really weird for me. You're back there saying, okay, so I wasted characters. I don't care. A, B, C, D, E, F, I don't care. I'm wasting that. But it's a really big deal to us as computer scientists to say, we don't care. We're actually going to waste for every BCD character in our system, we're going to waste 7 possible combinations for every single one of them. That's painful to say. But we have proven that its efficiency and performance outweighs the numbers of bits that are being wasted in a BCD representation. Therefore, we accept it. At least we accept it today. For those of you who are thinking about maybe your career is going to go down the research path, here's a great place. Right? How can you come up with numeric representations that's much more efficient than BCD? Right now, it's kind of big. It's kind of a big deal, but maybe one of your research topics will be something that replaces BCD because it hasn't been around forever. It's not going to stay around forever. You might be the one who becomes rich and famous for coming up with your name, coded decimal. Linda coded decimal. Doesn't that sound like a great number system? No, because my name's Edward. Okay. Edward coded decimal, or whatever your name is. Another thing to caution you about right now is because we've been focusing on these number systems, is that there is a difference between conversion, that is converting numbers, versus coding or encoding numbers. There's a difference between the two, and right now is the point where some of you are probably getting the two confused, okay? Because they're both very fundamental and very important in our ability to store numbers, represent numbers, and manipulate numbers inside of computing systems. Okay, so keep those straight when we're walking through each of these different examples and topics and you're working through these problems on exams. If we ask you to convert a number versus encode a number or decode a number, that's 2 very different questions. Okay? Similar words, but very different in what they're doing. Okay? So keep those separate as you're going through the readings and as you study and prepare for exams and such. Okay? And here's a couple examples. Right? converting 13 base 10 to a decimal number, and of course now you're all looking at it and saying, oh yeah, it's 1 times is base 10. 1 times 10 to the 1 plus
3 times 10 to the 0.
3 times 10 to the 0 is how you can represent it, but how do you convert that to base 2?
Divide it in half a lot.
How do I convert that to base 2? Divide by 2. What do I divide by 2?
13.
13.
Start with the whole integer part, right? Remember the algorithm. Now notice, this is another one of those rare implicit means implied, right? It's implied that there's a radix here because I don't have a decimal with a fractional component. So yes, this is another case where I might be able to imply it. So I have a whole integer part first. So yeah, I take 13 divided by 2. Remainder is 1.
6.
2, 0, 3, 2, 1.
1. 0, 2, 0.
What's that?
Remainder is 1.
Well, it's 0 with a remainder of 1, right?
Yeah.
This is the whole integer part. 1, and now, do I assemble it top down? Bottom up. So it's 1, 1, 0, 1, base 2. Yeah. 1, 1, 0, 1, base 2. From bottom up, reverse order, 1, 1, 0, 1, and that's my base 2 number. We're there. Look, we proved it. You thought it was hard. You're sitting there so scared saying, this is going to be hard to do. Whereas the first example that we walked through, where we said 1 times 10 to the 1, is how you could code 1, 3. If I want to use BCD coding, right, 1 in BCD is 0, 0, 0, 1, right? 3 in BCD is 0, 0, 1, 1. Conversion, coding. 2 different things. Don't confuse them. Yes?
Will we be focusing on several other different versions of coding for this class?
Well, there are some other coding techniques, now that you mention it. Let me jump right to those. There's probably the most popular one, but not the only one today, and that is ASCII encoding, where I could take 4 digits and I could represent these alphanumeric characters, these special characters, and what are these? Anybody know what these are called? Come on, you had 237. You used these. What were these called?
2 years ago.
2 years ago. That's ancient history. 2 years ago. Oh my goodness. Okay, we'll just call them special characters and move on. Just like these are special characters. All right, backspace, the bell. I know you're probably thinking, bell? What's a bell? Forget it. Space. Sub means to rub out. ESC for escape. All those different fun things there that you could tell your screen or your I/O device to do, or you're interpreting that those I/O devices are doing. Okay, so here's the control characters actually. Oh, darn, we'll get to spell it out for you. Here's the control characters actually spelled out for you, and you can use these today when you're doing your terminal I/O stuff. If you're working with curses or some other term I/O language where you are working directly with characters on the screen, you would actually use all of these different, or many of these different. That's probably a better way to put it. You would be using many of these different control characters in addition to escape characters, to be able to get the screen to manipulate your image for you to do what you want it to do. So yes, this is an encoding standard, American Standard Code for Information Exchange, or ASCII, that has been around for a while. It actually has a couple of versions. There's an abbreviated ASCII, except we don't call it that because it was the original ASCII. And the idea with the original ASCII was that bits were very, very expensive. Bits were very expensive. And so you'll notice here that in this version of ASCII, we're using 7 bits, right? These 4 plus these 3 to generate each of these alphanumerics, special characters, and control characters. Every bit, especially the early systems, was expensive. So an abbreviated version of ASCII, or the original ASCII, actually only used 6 of these. They didn't use 7, they only used 6. And to achieve that, one of the things that they did is they eliminated lowercase characters. And if you look at the difference between a lowercase a and a uppercase A, you'll notice that it's 100 versus 110. And the B, 100 versus 110, and so on. Okay? So what you're seeing is the difference of just 1 bit between all uppercase and all lowercase. Likewise, the differentiation between special characters and control characters had the same differentiation. So the early ASCII, sometimes referred to as abbreviated ASCII, only supported uppercase characters, the digit set, and some controlled characters, and some special characters. That way we could reduce the number of bits, given that we had very limited storage systems and even more limited communication systems, connections of computer to computer or I/O device to computer. That made a big difference. And so if you're looking at some early examples of computer I/O, and if you're looking at some really old computing languages where everything is in uppercase only, they're not shouting at you. Because I know when you're texting people and it's all caps, you're shouting at somebody, right? Well, in those early systems, it's because we were missing a bit. So everything was uppercase. That's why you'll see some of those older computing languages and examples of I/O systems in uppercase only. Okay, so that's ASCII. There are, let's see, I think there's another representation too that's very common today. UTF-8 encoding is another very common system that's being used even more and more these days. I'm not going to be asking you to specifically, like, from memory or anything like that, be able to do encoding between the two, but you might need to do it as part of an assignment at some point where you might need to work with an encoding system, and you certainly would need to be able to use the encoding system that we used earlier, BCD, right? All right. Questions on conversion versus coding? Got it? We have different representation systems or coding systems. I think we understand that. The other thing that we need to take away from here is that binary math is comprised of addition, subtraction, multiplication, and you notice I didn't put division there. But division is part of it. However, division can be accomplished by different techniques, right? You simply could multiply by the inverse power, and then you could just use multiply to do your division. Early computing systems, even some that's not so early, did not actually have a division operator inside the machine instruction repertoire. Okay, they would use multiplication, or they would use bit logic, bit masking to be able to do division. Okay, so there are other techniques other than just doing a hardware division operation to do the division with. So classic definition of binary arithmetic are these three, recognizing that you'll still do division one way or another, either through the hardware or by using bit masking or using inversion. Okay? So do brush up on how to do binary addition, binary subtraction, binary multiplication, should know about binary division as well. The reason why I say that is because we're focused on computer architecture, which means we're going to be focused a lot on logic. Logic is going to be done in base 2. Okay, so starting with chapter 2 onwards, we're going to be doing lots and lots of base 2 stuff. And base 2 to base 10, and sometimes 16 and 8. Okay, so you really need to make sure you understand how to do these operations, because you're going to do them with the logic diagrams, you're going to do them with the logic statements that you create. Okay? Now, here is something that we don't put in the topic of discussion at this level, but we need to. Okay, when I say we need to, it's because it's going to help you understand everything else that's going to come along in your subsequent courses in computer science, maybe some others as well. Okay, and that is one of the things that we're focused on in our discipline, computer science, is that of abstraction. And you're saying, wait a minute, we're talking about being specific, being able to describe things specifically, and I say yes, and we're going to use that language to create layers of abstraction so we can create complex solutions in software systems. Many of our software systems today are complex systems. We could not build them if we were writing them all in machine language. Having experienced the 237 class, you probably have some level of appreciation for that, right? It seems like it's pretty easy to be able to turn on a hexadecimal character using BCD, but it took you a long time to write that code to do it, right? So writing something like a browser or an operating system or a compiler or something simple like that is a lot of work, and it's not something you're going to do using machine level language. So we're going to create these different levels of abstraction. Likewise, we're going to create different levels of abstraction to talk about our hardware as well. And we already did, right? What did we say, what model did we say we were going to use for our computer architecture for this semester study? Von Neumann. We said we're going to use the von Neumann model, and we now can recite it, right? We know it has how many subsystems to it? 3 subsystems. CPU, my processor, right? That's a CPU, that's a solution. Processor, I/O, memory, right? Those are abstractions. Processor is an abstraction of a CPU, or the CPU itself is even an abstraction of an arithmetic logic unit, control logic unit, and register set, and maybe some cache memory, right? So we have these different levels of abstraction going on in our definition of our hardware, and likewise we have different levels of abstraction going on in our software as well, because we have machine level language. But you just sat there and told me that you didn't want to use machine level language to code up complex software systems, right? Instead, you wanted to use high-level language. Do you want to use a compiled version, or do you want to use it on the fly? Okay, put you on the spot. You don't have to answer that one. It's not a trick question, but it's a lengthy one, lengthy answer. So yeah, you have different kinds of high-level languages, and you haven't had your computer languages class yet, so you haven't learned about the 4 major categories and their pluses and minuses and stuff like that, but you're going to do that when you get into your computing languages class. Or maybe some of you are doing that in concert with this class. Maybe some of you have already taken it. But it's not required for this class, so I can't assume you know it. So that is a layer of abstraction, a computing language. And even computing languages, like scripting languages, how many of us have worked with, say, Python? Excellent. How many of us worked with shell interpreters? How How many of us have worked with JavaScript? Okay, so scripting languages, right? Scripting languages aren't something that you give to a compiler and it generates machine code that would then execute. Instead, it's going to go into a virtual machine which interprets the bytecode and does the work for you through this interpreter. It's running a simulation. It's a level of abstraction of the operating system running on top of the hardware. That's what those interpretive languages are doing. Okay? So these different concepts, these different levels of abstraction are important to us today because it allows us, it enables us rather. It enables us to create complex solutions either quickly as prototype solutions or in a very sophisticated, well-tested manner that can go to production software like your word processors and operating systems. Okay, so we have lots of different levels of abstraction. All we're doing is we're still doing things like flipping bits to ones and zeros, like we talked about at the beginning of the chapter, right? Because that's what the computer is doing. The memory system is storing these ones and zeros. The processing system is flipping them to 1 and 0 depending upon what the arithmetic unit or control logic unit is doing. Comparative, if you're doing comparative operations, it may also be setting them to 1s and 0s. And of course, your I/O subsystem is moving those 1s and 0s between your computer and the external device, or from the external device to the computer. It's all about flipping bits to 1s and 0s or interpreting them as 1s and 0s. But to help us create the tools to create more complexity, to create and solve more complex problems with, we come up with these different layers of abstraction so we can solve these problems in a manageable and meaningful way. We can create theories, we can create experiments, we can run them, we can generate data that we can analyze and create results with, and then maybe create something called a register or a microarchitecture, create some instruction sets, create a whole operating system, programming languages, algorithms, finite state machines, and application software, and systems of software, of a software platform system. All these different combinations are different layers of abstraction so that we can do more work either on our own or based upon work that somebody else has already done and integrating that with us, like we do when we compile our code using a compilation type of language or running it on an operating system. Okay? Levels of abstraction. It's very important to us, and you should be aware of that. I know it's not any of our documentation, and you're not going to find it in the course description of any of the courses that we teach you, but that's what we're doing. Okay? And it's a good thing. Without that, you couldn't create even algorithms. Right? Any questions? Yes?
Why is it that algorithm is more abstract than programming languages? I'm assuming it's a hierarchy, right?
This is a hierarchy, yes. So algorithms are going to need some programming language that you can implement it into to run and then do your analysis with. Without a programming language, you cannot study your algorithm other than from a pure mathematical point of view. And most of our algorithms that we're talking about are too complex for pure mathematical analysis. Great question. Other questions? Okay, I mentioned earlier you need to know 0 through 16 in the fork-based systems. And likewise, there's powers of 2 that you likewise should just know. Okay? Up to 2 to the 21st, really, I know I'd go all the way up to 23 here, but really up to 2 to the 21st is like the in your sleeve, right? You just rattle those things off, you know what they are. Some people know them up to even higher numbers than that, but typically when you're working problems as a computer scientist, you know 2 to the 21 and less, just right off the top of your head, okay? And we covered the representation systems, and that is it for chapter 1. Any questions? Monday, there's gonna be a lot more excitement